So as I was saying, the QCD is based on on the Yang-Mills theory, where the gauge group is SU3, and you can write down the Yang-Mills action for SUN, which is what I've written down. So the F mu nu is the gauge curvature. It's Lie algebra valued. So that means that this object here is should be thought of as giving you some element of the Lie algebra if you evaluate it at some particular point of space-time and you compute some particular component of it. And the gauge curvature itself is derived from the gauge field or the gauge potential, which itself is Lie algebra valued. And that's why you can write it as A times T, where T are the generators of the Lie algebra that you're interested in. For instance, you could use, if you used Gell-Mann matrices, the usual Gell-Mann matrices, then you would be talking about SU3. If you didn't, if you used some other group, then it would be the corresponding generator of that group. And this action actually has a what we initially describe as a gauge symmetry, which is that if you transform A in the way that I have written here, that is, there is an adjoint action of U on the gauge field A, and there is an inhomogeneous part. Then this action actually is invariant. So you get the A and U and the A that is transformed by U give you the same action. And you know that when you do a transformation like this, immediately you suspect that, oh, is there a conservation law? Because this looks like a continuous transformation. But gauge symmetries are a little bit different from symmetry transformations. In fact, gauge symmetries are actually a redundancy, and I think it is misleading to call gauge transformation as a symmetry, except under very special circumstances. We should remember that it's actually a redundancy. And because this is a redundancy, we would like to get rid of this redundancy, which technically we describe as saying that it needs to be fixed. So I'll tell you a little bit more about this in a bit. And so how do we go about dealing with Yang-Mills? You start off by looking at the writing. For instance, you may want to, if you're interested in the spectrum or the states, you would start off by writing down the Hamiltonian, for which you have to convert the Lagrangian to the Hamiltonian by the usual Legendre transformation procedure. So you calculate the momenta corresponding to the configuration space variables, which are A0 and the A's. And you can write down with a little bit of work, you can write down the Yang-Mills Hamiltonian. Of course, when you do this, you realize that something is a little bit off, because the momentum that is conjugate to A0 is actually 0. Just by inspection of the Lagrangian, you notice this. This should trigger a warning to you that the transformation from the Lagrangian to the Hamiltonian is not going to be straightforward, quite so simple as you imagined from from the simpler examples that one is familiar with. And that is indeed the case. And the origin of the fact that this transformation from the Lagrangian to the Hamiltonian is substantially more subtle is to do with that gauge redundancy that I told you about. So it turns out that because there is no momentum that is conjugate to A0, there is no the way the A0 appears in the Yang-Mills Hamiltonian is that there is no dynamics that you can give for A0. So whatever multiplies A0 is in some sense unchanged, never changes, and there's no way that you can change it under dynamics. So if there's something that doesn't change ever under dynamics, then we can in fact go ahead, we can call it a constraint. So that means all dynamics of Yang-Mills is constrained by this equation. In other words, the covariant derivative of the electric field, the derivative of the electric field plus this extra term, which we often call as the covariant derivative, is always set to 0 for any kind of physically allowed motion of Yang-Mills that you can think of. And if this looks a little bit mysterious, then I'd like to remind you that exactly the same thing happens when we study quantum electrodynamics. There are a few more bells and whistles. this equation here, that there is no momentum conjugate to A0, is there even in quantum electrodynamics. And there, of course, the gauge symmetry is symmetry under local phase transformations. Okay. Now, what I'm going to do is I'm going to look at Yang-Mills theory, and because we live in the real world, we live in 3 space dimensions with 1 time dimension, and I will allow myself a little bit of varying from the real world, which is that I will say that I will imagine my space as actually a sphere of a very, very large radius. So this is a slight liberty that I will take with the real world. So I will work with S3, the 3 sphere cross time, but I will for many phenomenological implications, I will take the radius of this S3 to infinity. So I'll go back to this. We'll go back to this case. And we will also work in something called the temporal gauge, where we can set so we see that the momentum conjugate to A0 is 0. The temporal gauge says that you can, because there is no dynamics for A0, I can choose A0 itself to be 0. So you have to do a little bit of work to show that nothing goes wrong if you choose temporal gauge. But yeah, and so you can indeed show that there are no contradictions, and then you proceed. Okay, so the playground, where you play this Yang-Mills game, is in the configuration space. This configuration space is based on on the set of all possible gauge fields. Now that A0 is gone, there are only 3 of them: A1, A2, and A3. And now let me tell you a little bit more about these gauge transformations that I wrote on my second slide. I said that these are transformations that you can do on the gauge field A, and nothing's supposed to change, in the sense that no physics is supposed to change. So let's make that a little bit more precise. So there are several kinds of gauge transformations you can do, and these you can do gauge transformations one after the other, and you can also compose them. So gauge transformations actually form a group. And if you look at the set of all possible gauge transformations, then one of the groups of gauge transformation, well, the group of gauge transformations that I'm interested in, is because this is the kind of thing that is important for connecting to real world physics, is that you look at transformations where you have a map from space, my 3-dimensional space, or S3 if I was working on S3, to the group SUN, such that this particular transformation goes to a constant value, constant element of the gauge group SUN at large distances, large spatial distances, it goes to a constant. So this is one of the groups of gauge transformations. The other one, which turns out important for discussions of canonical quantization, or to put it differently, for discussions involving the Hamiltonian and the states of the theory, is a group of asymptotically trivial gauge transformations, which is that it's a subset of this, in which you choose U to go to the identity element of this group. And you can show that this group, as the group of asymptotically trivial gauge transformations, if in addition is topologically trivial, then it is what is called the connected component of this of G infinity. I should have put in the G infinity here. And sorry, yeah, that's right. So this is a connected component of G infinity, and both G infinity and G infinity 0 are normal subgroups of this gauge transformation, group of gauge transformations. It can be. So I have excluded that possibility in this particular discussion. It is a very important, making it direction dependent is a very interesting and important direction that one can go in, literally as well as figuratively direction. Okay. So now, because we argued that if you just looked at A's, then there is redundancy. You don't want to count A's that are related to each other gauged by gauge transformations. You only want to count those A's. You only want to look at those A's that are unrelated to each other by gauge transformations. In other words, physically or gauge inequivalent A's. So one might think that if you take the set of all possible gauge fields and quotient out or identify those related by gauge transformations, then this smaller space, the space that remains, is the place where you will set up your dynamics. And that is a good guess, except that I'll show you, it's a little bit, the actual configuration space, if you want to discuss physical states, is a little bit different. And you can you can start off by looking at the Gauss law that I wrote earlier, which was here. This is the Gauss law. And one of the things that I do not have, unfortunately, do not have time to go in some detail is that because these are classical fields which you want to quantize, in other words, because these are quantum fields, the correct way to think about operator relations like the ones that I wrote, like the Gauss law that I wrote, is only if you smear it with test functions of appropriate type. If you fail to smear it with test functions, then the manipulations that you do, especially at points at, especially manipulations that involve the same space-time point, are confusing and difficult to do, and if you are not careful, can lead to wrong answers. Technically speaking, we just start off by saying that quantum fields are, right at the start of the game, we declare that they are operator valued distributions in order to avoid this possibility of making subsequent mistakes. We just say that they are operator valued distributions, and because they are distributions, you have to smear them by test functions. So if you smeared them with if you smeared it with a test function of this type, which test function which goes to 0 at large distances, then this is how you would write the form of the Gauss law. And see, even equations like this that I've written A and E. I haven't smeared it out. Strictly speaking, I should have written the smeared version of it, and then it would be rigorously equivalent. This is a formal commutation relation, but the other one would be is rigorously equivalent to this one. You can check that the Poisson bracket, or in quantum theory, the commutator of the generator of Gauss law with A is nothing but the covariant derivative of the test function. In other words, this is exactly the infinitesimal change in the gauge field under a gauge transformation. So you can check that G infinity generates gauge transformations.
So we have defined this curly G infinity by curly G0 infinity is SUI.
Curly, yes.
I just trying to understand what curly G is. Curly G infinity by curly G0 infinity is SUI.
Yeah.
In this case,
yeah.
But not always.
Yeah, it has to do with the question that he asked earlier about gauge transformations that depend on in the direction. So those are interesting and important and also new discussions. I think yes, that's right. So since I have only 75 minutes, I thought I would give you something that you don't have to mention. This is a prelude to what you will talk about. Okay. You can the reason why so you can check that the way I wrote down the little g infinity indeed generates a group G0 infinity, and this quotient is actually is just valued in Z. So it has disconnected component. I think I should have put a pi 0 here. There's a pi 0 there. So it has disconnected components, and this is a little bit aside. I won't have much. Will not have anything to say about it today. But these integers actually show up at a very interesting place. They show up in a discussion of what are called theta states in QCD. Okay, and the color group, of course, is G mod G infinity, which is SUN. Okay. Now, okay, so we've set up the machinery, but we would like to discuss also what are we going to measure, what are we going to observe. So for that, we need to understand the connection between observables and gauge transformations. Now, all observables, because they are observables, they cannot depend on what gauge you choose. So a more appropriate, the more correct way of saying is that observables have to commute with the generator, with the Gauss law, or they have to commute with gauge transformations. And this is very important if you're looking at local quantum field theories, which we should really look at only local quantum field theories. And there is a nice argument that a few years ago that Bal and I wrote down that has to do with looking at local observables. And it's not very difficult to construct local observables in Yang-Mills theory. In general relativity, it's much more subtle, much more complicated. But in Yang-Mills theory, it is rather straightforward. You take the quantum field and you smear it with a test function, whatever quantum field that you want that you have in mind, and you smear it with test functions that have only compacts that have support only in a compact spatial region. So the test function is non-zero in, say, in this room, and zero outside this room. This is, for example, an example of a test function having only compact support. And let's look at what happens when you do gauge transformations. So these gauge transformations, they act on this smeared on this such a smeared field only by the restriction of the action of the gauge of the U to this region. So if we are in this region and you make a gauge transformation outside this region, then it's not going to affect it. You have to use a U which is non-trivial in this room. So that's really the sort of unpacking the meaning of the statement, that it only depends on the restriction of U to the compact region that we have in mind. But if it depends only on the restriction, then we can extend this gauge field to whatever else we like outside. And in particular, you can extend it to gauge transformation U prime, which belongs to G0 infinity. So if phi is some observable in this compact region, then by Gauss law, it's easy to see that phi commutes with U prime, and therefore all local observables, local because they have only support in a compact spatial region, therefore commute not just with G infinity 0, but with curly G. And this was, I think, at least before we discussed it, people maybe knew it, but they had not said it out explicitly like this. Generally, the impression was that all you need for observables to commute is that it should commute with this group G infinity 0. But when you take into account locality of the observables, then the configuration space of the gauge fields is a little bit different. It's not A mod G infinity 0, but it's A mod G. Okay. So now that we have our configuration space, then the quantization is at least easy to it's easy to describe what you want to do. The actual process of doing the quantization is, of course, sophisticated and subtle. So you start off by looking at this A mod G. And if you're interested in wave functions, then these are wave functions that are if you're interested in physical states, then these are wave functions that are unchanged under gauge transformations. That is, if you make a if you make a globe, if you make a full gauge transformation, the wave function is unchanged. If you make a infinitesimal gauge transformation, then this wave function is annihilated by this the infinitesimal gauge transformation or the Gauss law. But you may, for some other reasons, be interested in wave functions that are colored, that transform non-trivially. So those would correspond to sections of vector bundles that you construct on, this should have been A mod G. No, sorry, this is correct, on A mod G0. So what we have is a fiber bundle from A mod G infinity G0 to the configuration space. And the structure group is just G mod G infinity 0. Okay. And once you have a fiber bundle structure, the question that one might ask is whether this fiber bundle is a trivial bundle or a non-trivial bundle. And this is important because then you would have to worry about whether you need to discuss wave functions by putting patches, or whether you can, or if it is trivial, then you can define the wave function in one shot over the entire configuration space. And the one of the most important results is that this wave function is non-trivial. This fiber bundle is non-trivial. It's a twisted bundle. In other words, if it was trivial, then you would be able to write A mod G infinity 0 as the base times the structure group, just an ordinary direct product. But there's a nice argument which was given, I think, in the late 70s by Singer and also Narasimhan and Ramdas, who showed that this thing that you might hope for is unfortunately not true. And I will give you I'll just briefly illustrate the argument that Narasimhan and Ramdas did, because I think that Singer's argument, while more general, is also very formal, whereas the argument of Narasimhan and Ramdas is at least from a descriptive point of view, more transparent. Oh, the Z is because I was looking specifically at SUNs. And so pi 3 of, so I think all compact simple groups have pi 3s to be Z. There was a pi 3 long ago. Here, this is that Z. Yeah. Oh, this one. Structure. This one. Let me try to think. He's asking why is there a Z here? Yeah. Yeah. These do you have this many disconnected pieces, no?
So roughly you're counting each one.
So you have to count them. Yeah. Okay. So the key idea of Narasimhan and Ramdas, they explored it for the simplest non-trivial gauge group, which is SU2. But it is very clear from reading their paper that it is a very straightforward generalization to any other SUN. So what they want to do is to prove that that bundle that we wrote is twisted. And they start off from a very interesting and a very key observation, in my opinion, which is that if you take any connection, any gauge field, then that can be approximated in a particular Sobolev norm with the Sobolev class greater than or equal to 3. That can be approximate arbitrarily closely by a left invariant connection. And when you say left invariant connections, these are actually just constants. These turn out to be just constants. So constant, the analog of constants on S3. So this is a remarkable fact that you have this entire gauge field, but in the Sobolev norm, it is you can always find a uh, a, 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 a Lie algebra valued constant matrix, I would say, that is arbitrarily close to this connection. And so first they show that you can approximate a connection arbitrarily closely. Then they show that the gauge group, similarly, which is an infinite dimensional group, can be approximated again in Sobolev norm arbitrarily closely by just SU2 in the add SU2 or in general adjoint action of SUN. And that observation they leverage into showing that this particular bundle can be written as a bundle of SU2 over left invariant connections, uh, with the base space being the quotient of left invariant connections by SU by the adjoint action of SU2. So there's a little bit of more work involved, but this observation of theirs, that you can find a left invariant connection that is arbitrarily close to any connection, is the key starting point. And this is also the reason why they argue that the topology of the full bundle, infinite dimensional bundle, is captured by this bundle, which is made up of only finite dimensional objects.
See why that is true topologically.
Yes.
There's a lot more information in a connection.
Absolutely, absolutely. So their aim is only the proof of a topological result. And this, if you like, this activity by approximating the connection by a left invariant connection involves throwing away a lot of information, like the kind that you mentioned, which is again true. So what they are able to show is that they, because of this, because of this observation of theirs, they are able to capture the topologically non-trivial part. So the matrix model approach takes this one step further and says, if we take this to be true, let us see how much more physics is hiding here, more than just the topological information. So I hope to show you that there is substantial amount of actual physics information hiding here, not just topological information.
Can you in principle expand on this?
So you will to do it right, you will have to see that a correction, some systematic correction to the left invariant form that you have is still sufficiently close. So in other words, we want to make an expansion of an arbitrary connection around this left invariant connection. And it is beyond my technical, and Bal thinks we can't do it.
It cannot be done because the connection is a distribution.
Yeah.
And what he is going to get is an ordinary function.
Yeah.
Okay.
Yeah.
When you're arguing about quality and so on, but A as an element in the function space.
Which the actual connect, the gauge field, yeah. Yeah, these are, I mean, in some sense, this is a classical argument. There is no quantum mechanics here. There's no quantum theory here.
What you do when you make it into a, so the idea would be that this can be derivated to a function of this time. Is that the idea? This constant.
That's right. So then this is your configuration space, and then the dynamics is the time that is there from before.
Can I make a remark?
Of course.
From what I remember about Narasimhan Ramdas, they said they were looking at an elliptic operator on a certain manifold with history. Yep. And ironically, the analysis of this elliptic operator involves Sobolev norms.
Yes.
Not missolutions. For example,
Yes.
this or the boundary.
Yes.
You need Sobolev norm. So that is how. But they were doing a classical situation.
Yes.
Come to this point.
Yes, absolutely. And that is how we most of the time in physics, when we are interested in topological considerations, we look at the classical configuration of whatever field you are interested in. whether it is a n component scalar field or whatever else you like. This is normally our starting point, right? So even for spontaneous symmetry breaking, the starting point is some group, and then it breaks to some other group, etc. So uh, yes, yes. And so their proof proceeds by looking at a special subset of these left invariant connections. And as Bal anticipated, what you can do is, I think I might have not, sorry, excuse me. Yeah, because I had other things to talk about, I took out that slide. But you can pull this using the Maurer, you can pull back, do a pullback. Using the Maurer-Cartan from on SUN or SU2, you can pull it back to S3, and what that gives you is just the curvature. And so, starting from the curvature, you can then construct for instance, you can construct the Yang-Mills action. So what they did is that at the end of the day, when all the dust settles, they showed that the fiber bundle that is at the core of this infinite-dimensional bundle, the non-trivial part of the fiber bundle is captured by this rather simple fiber bundle. That is SO3 action acting on the space of 3 by 3 matrices, and then the base space is the quotient of 3 by 3 matrices by SO3. The reason why this is SO3 is because gauge fields are acted upon by gauge transformations via the adjoint action, and the adjoint action of SU2 is nothing but the action of SO3. And with a little bit more work, well, I say little bit because it is a short part of the paper, but to unpack it takes takes some time. Narasimhan and show that this particular bundle is twisted, and because this bundle is twisted and it is an irreducible part of the full bundle, the full gauge bundle must also be twisted. That's yeah. So I did not mention the qualifiers. So they have to be rank 2 or greater, because if the matrix has rank less than 2, so that is 1 or 0, then this action is not free, and so then you get fixed points of so then. No, rank 2 or greater are good. So if it is rank 2 out of a 3 by 3 matrix, you can still have matrices of 0 determinant. But 2 is okay. So I need a watch to tell me how much time I have left. Shibashish. Okay. Okay. So I have. Okay. Good. Yeah. Yeah. So this is all because I am working on S3. Yeah. No, it makes the proof simpler, but there is a good reason to move from R3 to S3, because at the end of the day, we are interested in configurations that have finite energy. We may, I mean, of course, for example, we use plane waves all the time in our discussions, but they are a technical, they are a technical aid. At the end of the day, even if you may work with plane waves, you make wave packets which have finite energy. And also the whatever theory you have, the excitations that you can make or the excitations that you can study with maybe someone else had made are almost always a finite energy excitations. That that ideology, if you like, is captured very well by working on an S3 instead of R3. Okay, so the bottom line of the work of Narasimhan and Ramdas is that the matrix model corresponding to the gauge group SU2 comes from this matrix, this matrix, and this is just a 3 by 3 matrix. And as Rajiv reminded us, it should be of rank 2 or greater. But it turns out that you can allow the matrix to have rank 1, and it turns out that it is actually a very interesting corner of the gauge field. Because if you think a little bit about it, when you do when you look at a gauge field, there's no a priori reason to throw away reducible connections, because these correspond to reducible connections. If you, they can have reducible connections can have finite energy. So why should we throw them away? The question then becomes, where do they fit in the general discussion? And in my opinion, it is an interesting and important question of where the reducible connections fit. And we have some partial answers to that. So reducible connection is, so these are connections where the gauge transformations act freely. That is without fixed point, without, when you do a gauge transformation, it will give you a distinct one.
So holonomy is not dense in the group.
Um,
Holonomy is valued in the fiber, right?
yeah. So
If
that,
it is there,
yeah.
it is reducible.
Then it is reducible. So if the holonomy group is the same as the group of as the structure group, then it is called an irreducible connection. If not, then it is reducible. Basically, you have fixed points, and we should. But then it becomes, it is an interesting physics question. Should we throw away things? Should we throw away? What do you do at the fixed points? Are they physically interesting? Are they phenomena that correspond to the fixed point? And so on and so forth. So I will have, later maybe I will have a few comments to make about that. Okay. So that was for SU2, and it's all very nice, but if we want to do QCD, then we need to do SU3. And it's rather straightforward to adapt the discussion of Narasimhan and Ramdas to SU3, or for that matter, any SUN. So I will just tell you what one finds. So is that if you look at SUN gauge theory, then you work not with 3 by 3 matrices, but rectangular matrices, and those are your gauge fields. And then the gauge group of the gauge transformations is the adjoint action of SUN, and these are, so you want to quotient by these. So this is your configuration space. And it's not difficult to do some simple checks that this has dimension 2 into n squared minus 1. But again, you have to be careful at fixed points, places where there are fixed points, where the dimension of the space can change. But modulo that issue, which which we've all agreed is interesting and important, but modulo that issue, if you proceed, then wave functions are just sections of vector bundles that you write on this space, and that transform according to representations of add SUN. And if you choose wave functions that transform according to the trivial representation, it means that you're looking at colorless wave functions. So these are the ones that you would call colorless or physical states. And if you look at ones that are transforming non-trivially, then you would call them colored states. So the M's that are here, these matrices, 3 times n squared minus 1 dimensional rectangular matrices, are constant gauge field. I should have not said constant. I should have said left invariant. But I say constant because it's a little bit intuitively easier to communicate. They don't depend on the S3 coordinate anymore because they are left invariant. So they are constant gauge fields on S3. And this is the approximation. So this is an approximation of the full gauge field. And because they don't depend on the S3 coordinate, if you like, there is no information about how the gauge field varies from one point of space to another. So normally one thinks of this as momentum dependent information. So we've lost, or if you like, thrown away all the momentum dependent information. And so this is if you've thrown away all that information, then the only dynamics that is left for you is extreme low energy dynamics, because there's no momentum component at all. This is no, this is gauge independent statement. There's this. These are yeah. So if you these so under this gauge transformation now, they close. If you want to introduce even one YLM, then immediately the whole things escalates back into the full gauge theory.
Basically, this sort of an approximate. That's the sense.
That's right. So one can think of this as an approximation of the full Yang-Mills theory to at least aspects of the extreme low energy sector of the theory. Now you have to go and do some checks and calculations to see whether and how much of this extreme low energy sector of theory this captures. Okay. So but now because our game has become substantially simplified, we have just 3 by 3 or 3 by 8 or whatever matrices. These depend only on time, and we have to quantize the system. So this is nothing but a souped up quantum mechanical problem with many variables, 9 or 24 or whatever it is. But this is a quantum mechanical problem. The full field theory problem, we have cut it down to a quantum mechanical problem. And so now the quantization again is rather straightforward. This is the Yang-Mills Hamiltonian. After you do, I mean, I have dropped the term which I've chosen the gauge in which A0 is 0. So this is nothing but the square of the electric field, and this is square of the magnetic field. The Hamiltonian, as we know, is E squared plus B squared, and that's what I've written down. And then there is the Yang-Mills coupling occurs, one upstairs and one downstairs. But apart from that, we recognize this as what we write down, for example, in QED. And the way to quantize this theory is that we have these degrees of freedom, which are m's. We have the velocities, which are conjugate to m. And if you look at the Lagrangian, which I either wrote down earlier or I'll write down on the next page, then the electric field is just if you like, the velocity corresponding to m. So if you want to quantize this theory, you just impose this commutator. Commutator of m and e is a delta function. Okay, so sorry, this was so for example, if you wanted to look at what the Fij was now, the gauge curvature term, then you can calculate it by what I said earlier, by pullback of the Maurer-Cartan form. And in terms of m's, it has a rather simple expression. There's a quadratic term, there's a cubic term, and there is a quartic term. So this V, so in this quantum mechanical problem, I have just a kinetic energy term, which is like P m dot squared or P dot squared, and a potential V. And this V is gauge invariant. It is unchanged under gauge transformations. Actually, it is also rotationally invariant. It's not difficult to show that it's rotationally invariant. Okay, so you can do several things with pure Yang-Mills, which I don't want to go into. What I want to go into is whether we should add quarks, because it's only when you add fermions that it becomes closer to the real world. So I want to add quarks, and they are again rather easy to add in this case. We again look at quark fields, and you can make a somewhat rigorous discussion like how Narasimhan and Ramdas did, but the simplest thing is to just throw away the position dependence and just keep the time dependence of the quark field. So what kind of quark field, what kind of properties do we want for our fermions? They have to transform. If they are to be quarks, then they should transform according to some representation of the gauge group. For example, if they are to be quarks like U, D, or S, then they should transform according to the fundamental representation. There are other situations, interesting theories where the quarks may transform according to adjoint representation. You can choose what you like. You can add a mass term for the quarks or leave it massless. And you can add several quarks. And so in other words, you can add, you can have a flavor symmetry between the quarks, which is U and F. And so there are many things you can do and investigate this matrix model in several directions when you want quarks. So this is going to be a statement about the dynamics of the theory. At the moment that you set up the game, we cannot say anything. It is supposed to be a consequence of your dynamical investigation. So we will have more to say about it when I show you some dynamics. The proton should be bound, yes, and found, and I'll also predict its mass for you. Okay.
So the space dependence of the field was thrown away by hand.
For the quarks, I threw it away by hand. You can leave them space dependent. It is a consistent theory. Is more work. My principle is do as little work as possible and get as much information as possible. And I think in this I follow the spirit of condensed matter theorists, that take the simplest possible theory and get as much information as you can get from there. So if this doesn't give you enough information, then reluctantly we will go back and put the space degrees of freedom for the quarks. But yes, if you can put spatial dependence for the quarks and leave the gauge fields independent of space, and that is still a consistent truncation of the theory. Yeah, that is a statement about yeah, it won't affect the gauge bundle. Quarks are usually what are called associated bundles based on an original principal bundle. So
there's nothing that really says it has to be constant.
No. This is because we want to do some calculations.
How can you introduce space degrees of freedom when the gluons don't have any, and then you are going to kind of, how do they interact?
So you can think. So the intuitive way of thinking about it is that the gluons form like a background gauge field, which is spread out over all space. And so if you think about it that way, then you can see that the quarks can have space dependence, and so that's the way to think about it. Yeah. But if you look at massless QCD, the full quantum field theory, then it's known that if you have massless quarks, then these break something called a chiral symmetry. So I'll spend a few minutes telling you about the chiral symmetry and whether the chiral symmetry is captured when you look at the matrix model limit. And because whether it is captured or not becomes a very important consideration as to whether this is a realistic model for low energy physics. Okay, so let me briefly describe for you the chiral symmetry. Chiral symmetry and its breaking, which is called the chiral anomaly. And let's recall that an anomaly is a symmetry of the classical theory that you cannot implement in the corresponding quantum theory. And the chiral anomaly is one of the earliest and perhaps the best known example, and that's from massless QCD. So let me remind you what that is. So if you look at the Lagrangian of Yang-Mills plus Lagrangian of QCD, actually massless QCD, then you have the gauge field and you have the massless quark, and then the quark, which is described by a Dirac spinner, has these two symmetries, one which is called vector and the other which is called axial. The vector symmetry is just taking the Dirac spinner and multiplying it by a phase, e to the I alpha, and the axial one is you take the Dirac spinner and multiply it by a phase, but just before you make that multiplication, you sneak in a gamma 5 there. Okay. So because of that gamma 5, you remember that gamma 5 is what helps you distinguish between, for example, left and right-handed and so on. It's because of that gamma 5 that this particular kind of a U1 rotation is called an axial transformation. So this is called this is an axial symmetry. And if you look at the Yang-Mills Lagrangian, if you look at the QCD Lagrangian, then under either of these transformations, the Lagrangian is invariant, you can go ahead and compute the Noether charge and calculate the corresponding conserved charges, conserved currents, and so on. Excellent. There is a conserved current corresponding to this. There's a conserved current corresponding to this. So this is what I've written down. Classically, at least, the vector current is conserved, and so is the axial vector current. So this the small Noether's theorem type calculation gives you this as the vector current and this as the axial current, and it's trivial to check that it's conserved. What happens is that in the quantum theory, when you quantize the theory, but that is quantize both the gauge field and the quarks, then only the U1 vector survives as a symmetry, whereas U1 axial is no longer a conserved, is no longer the axial vector current is no longer conserved. In fact, if you compute the divergence of the axial current, then it turns out to be proportional to what is called the F wedge F term. Okay. So because this is in the where so here's F is a curvature. So it's no longer zero in the quantum theory. These anomalies are these peculiar situations that are very specific to this tension that you sometimes see between classical mechanics and quantum mechanics. And these we cannot wish away. They are facts of life. In fact, the fact that you can see this in QCD is in some sense the first and the earliest proofs that there are symmetries that are present at the classical level but are impossible to maintain at the quantum level, and therefore this is very much a fact of life.
This anomaly also, can we see that it's kind of like analogous behavior between classical and quantum theory and mechanics?
So this is actually precisely the place where the map that you want to make between a classical theory and quantum theory. So this is one of those arrows where you have to put a scratch. So so this is an example. This is an example of a symmetry, which is a classical symmetry, and on the other side, in the other column where you write the quantum theory, the arrow will go through. That is, there even in the quantum theory, this current is conserved. But this fellow is a symmetry in the classical side. But if you draw the arrow to the quantum side, you find that it's not conserved. So this is one of those things which does not map in the way that you would expect when you go from classical to quantum. So all the other things they map nicely. For example, the U1 vector.
It is actually a field theory because of the regularization.
Yeah. So that is going to be that is going to be my next slide, and you're referring to the folklore. Okay. So if you look at this anomaly, then the usual proofs of this anomaly involve field theoretic techniques, which you may, depending on which way you want to understand it, involves computing one-loop Feynman diagrams, regulating UV divergences, and finally, for instance, looking at the fermion measure in the path integral and showing that it is not invariant under the chiral transformation. And as TRG just mentioned, anomalies are often thought of as occurring, their natural setting is in field theories. That is, in systems that have an infinite number of degrees of freedom. Apart from the UV divergence itself, because one sees them in field theories, one also imagines that you need an infinite number of degrees of freedom. But what I want to show you is that this anomaly occurs in this quantum mechanical system as well. So this is a quantum mechanical system with finite number of degrees of freedom. For example, for SU2, the gauge field has only 9 degrees of freedom, and the quark will again have only 4 or whatever number of quarks that you have, that many degrees of freedom. And so you can see that I will show you in what precise sense that there is this anomaly. And because there is this anomaly, it has important implications for whether the QCD matrix model is a good model for low energy QCD itself. If the anomaly was not there, then there is no hope that the matrix model would have anything to do uh, with the real world low energy QCD. Proton spin is actually, I'm glad you brought it up because most probably I'll run out of time, so so I won't have time to say this. But there is an intimate connection, for instance, between anomaly and proton spin. Yes, 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 absolutely. Uh, Okay, so I will argue that there is an anomaly, literally imitating the technique from the discussion from quantum field theory. So, what do we do in quantum field theory? These are the steps that we take. You start off with the Euclidean formulation, and you look for instantons. So, just as in the case of just as in the case of the field theory, you can classify them as self-dual or anti-self-dual. Then take any one of these instanton backgrounds and couple to it a single massless quark. It's is straightforward to generalize it to more flavors, and look for the normalizable zero modes of the quark in this background. All these things are exactly what you do in field theory also. Then, because this is a zero mode, you can look at how this zero mode, you can study the contribution of this zero mode in the fermionic path integral. And we will see that this contribution of the zero mode to the fermionic path integral is not invariant under axial transformation. This is exactly what Fujikawa did also. So if you look at zero mode, if you look at modes that are non-zero, then their contribution to the path integral is indeed invariant under axial ones. It's only the zero mode that creates trouble for you. And finally, it's a small step from there to argue that the corresponding chiral charge is not conserved.
Again, essentially the regularization plays a
Okay.
Here you have only finite.
Yes. Yes.
So there's no question of regularization issues, right?
There are no questions of regularization issues.
So
No.
I should.
Two more slides. Yes. 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 And you can have parity anomaly in particle on a circle and so on. Tejas is just giving me a hard time. He knows all these things. Okay. I will tell you in 2 slides. Bal, you wanted to say something?
Anomalies are just changing the supersymmetry rules, nothing more. That's what happens. So even a particle in a circle, this happens.
Yes.
There are
Yes.
or parity
That is why I said you know all this. You're just giving me a hard time.
anomalies in a particle in a circle, if the wave function is quasi-periodic.
Yes.
It's very simple.
Yes.
So it is a mistaken impression that anomalies are subject to
Yes.
quantum field.
Yes.
It happens in quantum field theory, but it happens in all kinds of other problems.
Yes. Yes.
It's-
But can I give a complicated example instead of a simple example?
Of course.
Yes.
Particle in a circle, most people could maybe.
Okay. And so, of course, there are some important differences compared to the full field theory case. And as a byproduct, we have a variation of the index of the Atiyah-Singer index theorem. Yeah.
Basically, you're trying to say that just by using the matrix model, you still have your kind of anomaly preserved, and so you can go ahead with.
That's right. Because if the chiral anomaly was not present in the matrix model, then it would tell you that then chiral symmetry would be good. Then corresponding to a pion, I would have another particle of the other handedness, other chirality of exactly the same mass, which is completely wrong as far as our universe is concerned. So then this model, whatever its virtues are, would have nothing to do with the real world, and it would be there is hope now because chiral anomaly is present. There is hope that it captures, and this hope I will show you actually translates into numbers. Okay, so let me introduce the quarks. Like I said before, take a quark field and just throw away the space degrees of freedom. And these are just Grassmann objects that depend only on time now because I've thrown away the space degrees of freedom. And they transform under rotations and under gauge transformations, like I've shown here. Yeah, I've taken the gauge group to be SUN, so it'll work for SU2 and SU3 also. You can write down the Dirac-Lagrangian. It probably requires no explanation here. And finally, because we are looking at the path integral picture, I'm going to Wick rotate, like I've shown here, and that is going to give me the Euclidean action. Or I was hoping to not talk about it. So it comes if you look at the Dirac field on S3, then that is a term that there's a coupling to the curvature. So that's all. Yeah. So if I had introduced all the dimensions, then there would be a 1 over R. Okay. So if I look at the Euclidean action corresponding to the Yang-Mills, then this is what it looks like. Again, it is just E squared plus B squared. This electric field is not quite the same as the electric field that I had written down in real time. But that's because of that Wick rotation that I've done. So we shouldn't, I'll just call it the Euclidean electric field, or sometimes not use the word Euclidean, but that's what it is. And then the B squared is of course exactly the same as it was before. So if I want to look for minima of the action, classically at least, then I would want the electric. I would want, for example, this action is a sum of two positive terms. So this would be, for instance, this would be 0 if each of them would be 0. In particular, I would want, for example, to be for the B squared to be 0. But B squared looks like this. This M, there's a linear term, and then there is a term with the commutator. Okay. This was also what I had called earlier as V. So whenever V is 0, then the trace of B squared is 0. But V is 0 when the M's obey a relation like this. That commutator of M1 with M2 is IM3, etc. And for the fuzzy sphere aficionados in the audience, you immediately recognize this as the equation of that is central to the discussion of the fuzzy sphere. But for everyone else, we recognize this as the equation obeyed by the angular momentum algebra. So what are the solutions to these equations? Because we already learned this long ago in our undergraduate physics, the minima, or equivalently the solutions to this equation, are simply when you choose the M to be generators of the angular momentum. So where the M is some n-dimensional representation of SU2. But from this discussion, nobody told us that this representation has to be irreducible. They can be reducible, and that will give you, if you choose a irreducible one, it's one solution. If you choose a reducible one, it's another solution. If you choose a different reducible one, it's another solution. Yes. Oh, this is SUN. Okay. Now this is the Yang-Mills action, Euclidean action, E squared plus B squared. No, so these are yeah. It turns out that the minimum of the B squared term is given by this algebra. So that's where the SU2 sneaks in a somewhat unexpected way. Yeah, somewhat unexpected way. So because otherwise, if you just think of SUN, then there's no natural place for it. There are many places that SU2 comes in, but this is an unexpected way that it sneaks in. Okay.
Any subgroup of SUN, because all that you're using is epsilon.
Yeah.
You can replace it with F.
No, it has to minimize trace b squared.
So F squared has similar properties to epsilon. I mean, what you're using is epsilon contraction, the bunch of delta functions.
Sorry, I don't know. You're saying I can use any representation of?
Take SUN, take a representation. I'm not sure about this.
Uh-huh.
Take a representation SUK inside that.
Huh.
Okay. Take the SUK structure constant there.
Huh.
I think it will still work up to normalization.
I don't know that it will minimize. It won't, b squared won't be 0. Trace b.
It has to be epsilon ijk.
It has to be epsilon ijk, and this epsilon ijk came from the sphere. Yeah.
I'm trying to take epsilon contraction into finally delta function. That's why you cancel the M. Right? That equation.
Okay.
Square M complicated with M. Square. Take it to we get something proportional to the M.
Oh.
That comes from delta function of the epsilon.
Hmm.
So if you replace this epsilon by the structure constants of say SUK in SUN,
Hmm.
with maybe some normalization and I don't know.
Hmm.
I think it will still happen.
We will check. Yeah, we can check. Okay.
This kind of formula has come in string theory.
I have not kept up. I think Meyer's effect, it came up a long time ago. But let me just go on, because I think at some point Subhashish is going to yell at me. In 10 minutes, he is going to yell at me. Okay. So if you look at this identity, then you can put a bound on the Yang-Mills action. Again, this is rather straightforward. So this bound, this greater than equal to sign is saturated when E is equal to plus or minus B. And the advantage of working with a solution with this condition is that this is first order equation in the tau, first order differential equation in tau. So this is the equation that we would like to solve. So equations like this have occurred in the discussion by Nahm. So Nahm's equations, for example, this term, if you drop this term, then m dot equal to this is nothing but the Nahm equation. Okay. So so now I have turned back the electric field on, and I'm the Euclidean electric field, and I'm looking for solutions of this equation. The simplest case, of course, for example, if you look at SU2, then there are two degenerate minima. When the m is just 0, or the m is proportional to the spin half representation of SU2. So these are the two minima, and you can write down the instanton and the anti-instanton solution that tunnels between these two solutions.
Can I ask you a question? Nahm equations are dimensional directions of monopole equations.
Yes.
Where are the monopoles here?
We can we can discuss that later. I merely pointed out that if you drop this term here, then this is exactly Nahm equation. Whether now you can unpack it in a different direction to find a monopole would be very interesting, but I do not know. I haven't thought about it.
So just to understand, so this you could also have MIs which are different representations.
Yes, absolutely.
Then you would have the interpolation.
Absolutely. Very good. Very good. You anticipate my next slide. Okay. So this is a picture of the instanton and the anti-instanton. It's just this function that I've plotted. So they go from 1 to 0 and 0 to 1, and they interpolate between the two solutions that I showed you for the case of SU2. But the same interpolating field can be used in any other for SU3, SU4, any other SUN. And in general for SUN, if you're looking at self-dual or anti-self-dual solutions, you can choose any initial set of J's as the initial configuration, and some other set of J's as the final configuration, as long as they don't get entangled with each other. So that's a statement that their commutator is 0. So each of these, the starting one and the ending one, what we do, what one can do, because it is turns out to be useful in the future, is that you count the number of irreps that are there here and count the number of irreps that are here. So keep that number in mind. It is some integer. Keep it in mind. It turns out that the instant that if you compute the instanton number as this integral trace e dot b, then you get a formula like this, which turns out to be an integer, but by itself it is rather this thing mysterious or not very illuminating. So you can do the following. Uh, for either the instant or the instanton, you can construct this instanton charge that is expressible only in terms of the r's that I defined earlier. The r is the number of irreducible representations either in the beginning or at the end. So there is an r for the beginning and r for the end. And these two r's, in terms of those two integers, you can write down this instanton charge. And with a little bit of work, you can show that this instanton charge is nothing but the difference between those two integers. So the new instanton charge is still an integral over total time derivative and hence a topological invariant. If you don't want to go through this messy business of rescaling and all, you can just define this R02 and R01 as the instanton charge of the initial configuration and the final configuration, because these depend only on the gauge field. They don't depend on anything else. Okay. Then the process is a little bit long but straightforward. You start off from the fermionic action and you compute the eigenvalues and eigenfunctions of the Dirac operator. They come in pairs. There is a psi and gamma 5 psi. If the eigenvalue is not 0, then psi and gamma 5 psi come in pairs. So if one of them has eigenvalue lambda, the other one has eigenvalue minus lambda. These are, of course, when the eigenvalue is not 0. But you can also have eigenfunctions with 0 eigenvalues. Those I have written down like this as chi's. And so the 0 eigenmodes plus the non-zero eigenmodes, that whole set together forms a complete set. And in the instanton background, you can write so the whole idea again to you repeat the field theory calculation is to choose an instanton background, and in that instanton background compute prove the index theorem, so to speak. Okay, so you look at the Dirac operator in the instanton background. So that's why I have put a J here, because that's what the instanton is. Corresponds to a particular minimum. And then there is a very nice theorem by Calais, which is called the index theorem for open spaces. So there is a very simple application of the Calais index theorem. And that tells you that for Dirac operators of this type, you can compute the index of this Dirac operator. And for our case, it works out to be of a particular form like this, which let me just show that I have just 10 minutes left. So let me just quickly hurry through the calculation and show that if there are nr minus 1 normalizable zero modes for D slash with one chirality, and there are none if you are looking at either the instanton or the anti-instanton background. And there is a little bit of extra discussion you need to do when the size of the block is 1, which I will skip for the moment. But if you then define the index of the Dirac operator as the difference between the number of zero modes and zero energy resonances with positive chirality and the negative chirality, just define the index as this, then it turns out that the index theorem works out to be precisely this, that the index of the Dirac operator with the self-dual background is equal to R2 minus R1, or If it is the anti-self dual background, then it's with a minus sign. So this is the matrix model version of the Atiyah-Singer index theorem. So we find that there are zero modes for the Dirac operator. The zero modes of the Dirac operator are exactly in correspondence with gauge data, which is captured by R2 minus R1, and it counts the number of zero modes of opposite chiralities. And this is what just finish the last sentence. So this is what is remarkable is that we did not expect that we would find an index theorem for this situation. At some level, we didn't expect, but having found it and we knowing that you can find anomalies in quantum mechanics, it is very satisfying to have found that the index theorem still survives in this context.
Yeah, so since the index is actually computing sort of a difference between the numbers.
Yes.
So, but in the full Yang-Mills theory, it is more of a winding number.
That's right. And so this, as I said, that there are some differences compared to the usual discussion. And yes. Determinant of the Dirac operator. Yes. I don't use the determinant of the Dirac operator, but a very close argument related to. So the last step. So that this you might say is just index theory. Some might argue is just math. But the connection to physics is, in some sense, coming from showing that the fermion measure is not invariant. So yeah. So it is in the fermion measure that the determinant of the Dirac operator comes in. So that's what we show. And so let me just promise you that all these manipulations are good and checked many times, and you can show that the measure now when you do this in the path integral, when you make a chiral transformation and the measure changes like what I've shown, and this object A, I think, is exponential, essentially the exponential of the determinant. Captures for you just the difference between the number of left and right movers. So there's one regularization TRG that you need to do, because this object is somewhat is by itself difficult to make sense of. So you interpret that object by putting a e to the minus beta d slash squared, and then take the limit of beta going to 0. So you can show that with a little bit of work, you can show that that term boils down to just the difference between the number of positive chirality and the negative chirality guys. And therefore, you find that the integrated version of the anomaly gives you the difference between n plus and n minus. And in fact, if you this alpha that is here is the angle by which you did the rotation. So if you choose the angle right, for example, if you choose it to be n pi, then the anomaly vanishes again, which is known that when it is interpreted, you can understand it by saying that the residual symmetry U1 is broken to Z2. You can see that here. And if it is NF flavors, so I showed it to you for one flavor. For NF flavors, it is Z2NF. You can play the same game with adjoint fermions. Oh, you make a chiral rotation. You make a chiral rotation. Here, this is in general depends on tau. Then you restrict to a constant chiral rotation, and that is at alpha. So you can do the same discussion for adjoint fermions also, and again you find that the chiral symmetry is broken. And if it is a single adjoint Weil fermion, then axial symmetry is broken to Z4, not Z2. For NF is broken to Z4NF. Okay, so this was if you like, the anomaly part, and now I will 2 minutes. 2 minutes. In 2 minutes, I will show you that with this model, you can do variational calculations and you can do computations which, based on how much manpower and computing resources were used, is competitive with lattice results. So the whole idea is to take this Hamiltonian. It's now a Hamiltonian which is just a finite dimensional quantum mechanical system, and there are cubic and quartic terms. So it is a harmonic oscillator with cubic and quartic terms whose energies that you would like to find. And so you set up the variational method by constructing a trial set of only colorless states, or if you want to look at of only colorless states, and then the colorless states you organize by spin and flavor. So you have colorless states of spin 0, spin half, spin 1, etc., and further organized by flavor symmetry. So the model that I have is the Yang-Mills model based on SU3, and I have 3 quarks now, U, D, and S, and I have added the mass term. The mass term will get fixed based on some subsequent discussion. So in our variational method, we had for mesons of about 450 states, and for baryons about 1,000 states. And in the trial set, so in the variational method, you have to use a trial set. So this is the kind of wave functions numbers that we had to play with, and you have to do a certain amount of work in order to match with the real world. So G, R, MS, and MUD, these are the 4 parameters that have to be fixed. And to fix these 4 parameters, we have to sacrifice the known masses of 4 particles. So the 4 particles that we sacrificed were M pi, M rho, M lambda, and M delta. And let me just show you the predictions that we got. So these are the masses of the mesons, and these are the masses of the baryons. So you can see that for k plus minus, k0 bar, for eta and for eta prime, we've done quite badly. This is with 33% error, this is with 75% error, and this is with 45% error. For eta prime, and k plus minus, k0 bar. The others, k star, omega, and phi, we do quite well. This is with 8% error, this is with less than 1% error, and this is about 14% error. These are the mesons. And by mesons, I am including the pseudoscalars and the vector mesons. Then I look at the baryons, and with baryons, I do much better than I do with mesons. The worst case is with omega minus, where the error is about 11%. Proton, TRG, is just 0.3% error. But so I can elaborate a little bit about this, because if you change the particles that you sacrifice, I chose those 4 particles. If you play around with those, then these error bars can change a lot. So I chose we played around with many of them, and we chose the ones which gave the least chi-squared deviation. No, we chose these to sacrifice. Yeah. We can discuss this. Yeah, we can discuss this. What we did was to compute the chi-square deviation for the entire set, and this particular one gave the least chi-square deviation. We are not in this game, so we don't know whether this is our naive idea of the schoolboy idea of what is right.
So the eta prediction, for instance, is it how good is the eta prediction of the lattice?
I will tell you about lattice. Yeah, 2 weeks ago, a lattice specialist came and he was telling us again about these kinds of predictions. They get it within 2 to 5% error, but they set the pion mass to be 450 MeV. We chose it to be the pion mass from the particle data book.
So, but if you do the sums of something,
I know, I didn't try that. But Yeah. With only two flavors, we are left with we don't even have vector mesons, right? Yeah. But just U and D. So we'll have to, but we'll still have to sacrifice 3 points. We could, but yeah. So
Phi as a pure SS state, I think.
yeah, that is what happens with this trial set. We find it as a pure SS bar. We are not getting that mixing. So yeah. But there are other this in the eta prime part. We are not getting the right mixing at this level. No, eta prime is very bad. 75% and 45%.
No, that is your error. But mixing between
No, yeah.
the singlet is very small.
Yes, it is. But
Phi is almost a pure SS
yeah, but uh, so there may be several reasons. One is that maybe we need to go to a bigger trial set. So the effect of the anomaly is not being correctly captured. So anomaly is what is responsible for the masses of eta and eta prime. So we have to see whether we need to make the trial set bigger. Yeah.
Even for eta phenomenon, eta prime I can
Yeah.
Eta prime are mixtures of SU8 and
Yeah.
sorry, the octet and
Yeah. So they will have.
some combination is really the one that is getting.
That's right.
10% mixing.
Yeah.
So then do you get the eta correct better than the eta prime? Because eta has very little of the.
Yeah. So we have. So this is our eta is degenerate with the pion. This is our prediction. We can't do better than that. Okay. So let me just quickly tell you about the proton spin. And we know that about in the mid 80s, there was a result that came from European muon collaboration. And they looked at how much spin of the proton was carried by the quarks. And to their surprise, they found that it was almost zero. Subsequent experiments and reinterpretations of some of the older data has now put the quark contribution to be around 4%, or between 4 and 20%, depending on which data set you use and which experiment you look at. So I'll quickly show you what we found in a simpler model, which is an SU2 matrix model. And we use a simpler model simply because there's a lot of numerical work that needs to be done. But already at this level, we can see. And we've coupled just one flavor quark. So this is a QCD 2,1. And here we find that at strong coupling, there is a very significant contribution to the total spin of the particle from the glue. And as a byproduct, we also recover what is called the Isgur-wise heavy quark symmetry. That is, when the quark becomes very heavy, the entire spin of the particle resides just with the quark, no contribution from the glue. So that's one way of stating Isgur-wise heavy quark symmetry. So let me just show you some pictures. Sorry about that. Okay, here it is. So in this model, there is a particular sector which has baryon number 1 and spin equal to 1. So we call this BJ,1 sector. And in this sector, we look at how the total spin, which is 1, is distributed between the quark and the glue. So there is this parameters in the Hamiltonian called the chiral chemical potential. And if the chiral chemical potential is smaller than a critical value, then the quark contributes significantly. And if it's greater than a critical value, then the glue contributes significantly. So you can see the L squared is the square of the glue angular momentum, and S squared is the square of the quark angular momentum. And there is a jump here at this critical value of C. On the x-axis is the C, which is called the chiral chemical potential. But specifically, if you look at the Z component of the quark spin, then at 0 mass, we find that below the critical value, the quark contributes 2/3, and above the critical value, the quark contributes 1/3. So you can see that above the critical value, the glue contributes 2/3 to the spin, but even below the critical value, the glue contributes 1/3 to the spin. So this is not quite QCD because it is SU2. There's only one flavor, etc. But already you can see how the mechanism is going to operate when you do QCD. So and finally, although I don't have time to show it, we can see that if you take the quark mass to be very large, then S3, the the Z component of the quark, is almost always 1, which is how it should be. So there is no contribution of glue at all in this. And this is, if you like, a version of the Isgur-Weiss heavy quark symmetry, which anybody who has gone through Syracuse knows a lot about heavy quark symmetry. And okay, so I'll end here. This is my summary slide, and I'll just leave it here and not say anything more because Subhashish has been very kind to me. Thank you very much for listening. I'll flash the thank you talk, but thank you slide, but go back to the summary slide. And sorry for taking some extra time.
I just have one comment on the proton spin. The sum of the quark and gluon contributions need not add up to 1. Because there is orbital angularity.
Yes, so
The second point is that the gluon spin contribution has been measured by Rick.
by
Rick.
okay.
So the number.
Okay, I would very much like to ask you for the reference. Tell me the. Okay, fine. Okay. Okay, so okay. So this is there is a lot of discussion about. So there is the intrinsic spin of the quark, the intrinsic spin of the gluon. Then there is the angular momentum of the quark. People also worry about the angular momentum of the gluon. And there is a lot of discussion and argument about how much is contributed by what. So so there is a lot of discussion, and from what I read, not all of it is not most of it, but not all of it is friendly. This discussion. Yeah. Thank you.